Have you ever stopped to think about how computers do, well, everything? From booking a train ticket to playing a game of chess. It really feels like magic, but underneath it all, there's a super logical process. Today, we're going to pull back the curtain and decode that master plan. Let's jump in and learn how to solve any problem like a computer.
And this quote is the perfect place to start. It says computer science is a science of abstraction. So what does that even mean? It means it's not really about the machines themselves. It's about building the right model for a problem. Kind of like creating a simplified map that just shows you what's important. It's actually a really creative way of thinking.
Okay, but here's the big secret. The main idea for this whole explainer. Computers on their own can't solve a single problem. Not one. They're basically just incredibly fast and obedient tools that sit there waiting for us to give them exact step-by-step instructions.
So, how does anything get done? It happens through this universal four-step master plan. You start by really analyzing the problem. Then you create a blueprint for the solution. That's called an algorithm. Only after that do you start coding. And then you have to test everything like crazy. This is the roadmap for turning any problem into a working solution.
And that brings us to the most important word on the table. Algorithm. You hear it all the time, but what is it, honestly? Just think of it like a recipe. It's a set of exact step-by-step instructions. If you follow a good recipe for a cake perfectly, you get a cake. A good algorithm is just like that, but for a computer.
See, for us, riding a bike feels pretty intuitive, but a computer has zero intuition. Its instructions have to be brutally precise. Look at that recipe on the right for finding a square. Get a number, multiply it by itself, and show the result. There's absolutely no room for guessing or misunderstanding.
So before programmers write any actual code, they sketch out their recipe. They often use something called pseudocode, which is basically just plain structured English, or they'll draw a flowchart, a visual diagram of the whole process. You can think of these as the architectural blueprints for the solution.
And these blueprints have their own simple language. An oval means start or end. A rectangle is an action, like a calculation. A parallelogram is for getting input or showing output. But the diamond? That's where things start to get really interesting. That's for making decisions.
Because let's be honest, most problems aren't a simple, straight line. We constantly need to make choices. And a lot of the time, we need to repeat the same tasks over and over.
Now, to handle all that complexity, it turns out that pretty much every algorithm in the world is built from just three basic structures. Sequence is just that straight path, one step after another. Selection is the fork in the road, that's our diamond shape. And repetition, which we call a loop, is for doing something again and again. Let's make this real with a classic problem, a lamp that won't turn on. A computer can't just figure it out. You have to give it a logical path. So the very first step is to ask a simple yes or no question. Is the lamp plugged in? This is a decision point, a selection. And if the answer is yes, it is plugged in, well, you still haven't solved the problem. So you have to move to the next logical question. Is the bulb burnt out? You can see how a series of these simple, binary choices guide you through the problem until you finally land on the solution. But what about all those repetitive tasks? Like, say, adding up 5 different numbers. I mean, writing out the same instruction 5 times would be super inefficient and clumsy.
This is exactly where repetition becomes a total game changer. To average these 5 numbers, the main task, getting a number and adding it to a running total, is exactly the same for all 5 inputs. This is the perfect job for a loop. To build that loop, the first thing we need is a counter. So we'll just create a little variable, we'll call it count, and we'll start it at 1.
Next, we give the loop a condition so it knows when to stop. We tell the computer, keep repeating the task of getting a number as long as our counter is less than or equal to 5. The second the counter tries to hit 6, the loop just stops automatically. It's incredibly efficient.
So we've analyzed the problem. We've designed our algorithm, using our building blocks, sequences, selections, and loops. Now, and only now, is it time to translate that blueprint into a language the computer can actually understand and execute. And that translation step, that's what we call coding.
But just because you've written the code doesn't mean the job is done. Not even close. There's a famous saying in programming, garbage in, garbage out. All it means is that a program is only as good as the logic you put into it. If your recipe is flawed, you're going to get garbage results. This is why testing is absolutely non-negotiable.
Let's look at a really clear example. Here's an algorithm to add 2 lengths of time together. The logic seems simple enough. Add the hours together and add the minutes together. Makes total sense, right? But watch what happens when we test it. If we add 4 hours and 50 minutes to 2 hours and 20 minutes, our algorithm spits out 6 hours and 70 minutes. Oops, that's not how time works. Our logic is flawed because we completely forgot to handle what happens when the minutes go over 59.
So, how do we fix this? It's actually really easy. We just add one of those selection steps, an if statement. Our new corrected algorithm says, if the total minutes are 60 or more, then add 1 to the hour total and subtract 60 from the minute total. That one little logical check fixes the entire problem.
Now, this whole process, analyze, algorithm, code, test, it works perfectly for these kinds of focused problems. But what about something truly massive? How would you even begin to design something as complicated as an entire railway reservation system?
And the answer is, you don't. You don't solve it all at once. You use a super powerful strategy called decomposition. You take that massive challenge and you break it into smaller, more manageable pieces. Different teams can solve each part on their own, and then you integrate all the solutions at the end. It's really the only way to build something big.
As Howard Raffa put it so well, you decompose a complex problem, get one's thinking straight, and put these analyses together with logical glue. That logical glue, that's the master strategy for tackling any challenge that feels totally overwhelming. So, whether it's designing a perfect step-by-step recipe, using logic to navigate choices, or breaking a massive challenge into smaller pieces, you now have the toolkit to think and solve problems just like a computer. Which, of course, brings up one final question. What complex problem in your life could you solve by just breaking it down?